on this recording, this is the sheet that we talked about that has kind of the wordy stuff, right? Are all collisions successful? No, they have to collide with enough energy and proper orientation, right? What is that energy called? Activation energy. They create the activated complex or transition state. The catalysts are not used up in the reaction. How does a catalyst line look on an energy diagram? It should be below because it lowers the energy one, but we usually don't write it as a solid line. We write it as a dotted line, right? Good. This test used to actually be all written. So this is going to be a new experience for me to write this test for you. Not a fun experience, but we'll see. It used to. All right, so let's take a look. As the reaction occurs, the amount of concentration of reactants does what? Decreases. Can you guys see this okay? Decreases. Excuse me. And the amount of concentration of products does what? Increases. In order to determine the rate of reaction, you could measure a blank during a particular blank. What is it? A rate actually is what we want to measure. So a change during a particular what? What is a rate based on? Time. Right? So a change in concentration of reactant goes down, or a change in concentration of product going up. Right? Just keep those in mind. So a change in reactant concentration going down over time, or a change in product concentration going up over time. You could measure either one. For example, what did you guys calculate? You calculated the formation of sulfur over time, right? That was a change that you guys saw. But a lot of these things we're looking at is the decrease in reactants sometimes, right? Factors that affect reaction rates are temperature, concentration, that also does the volume, whoever said the volume earlier, and surface area. Those are perfect. Given a rate law, R equals K, A to the M, B to the N, what is necessary to determine the exponents? What did we always have to determine any of these things? We had to have what? We had to have a table with data. If a reaction is third order with respect to A and first order with respect to B, what is the rate of law of the reaction? Rate equals K, A, B to the what? Third. What is the overall order of the reaction? Oh, I'm sorry. That slipped it in my mind. A would be 3 and B would be 1. What is the overall order of the reaction? 4. If I double the concentration of A, what happens? And I leave B alone, what happens to the rate? Yeah, it would be 8 times faster, right? But what if I double the concentration of B and leave A alone? It just doubles. What if I double the concentration of both? 16 times more, because we would take that to the fourth, right? What if I tripled both? Then it would be, no, not 4 to the third, 3 to the fourth power. So 27 times 3 times 3. Or is that 9? No. Yeah. Yeah, so it'd be 81. Good. Yeah, right? It'd be 81 times faster, right? So basically, you take a look at the order overall, and then if you double everything in there, you take that doubling to the fourth power. According to the collision theory, this is also called kinetic collision theory. So sometimes you'll see this instead of reaction rates review, you might see this as kinetics review. According to the collision theory, two things must happen in order for a reaction to occur. What are they? Right, reactants must collide. Reactants must collide. With proper orientation and enough energy. What is the activation energy? It's the minimum amount of energy required. Minimum, an A, I don't know. Minimum amount of energy needed to form what? Nope. 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 These are the problems that are going to get together. What's in between reactants and products? Nope.
Reagent.
Nope. Reagent's just another funny term for reactants.
Is it like equilibrium or something?
No. It's amazing. What's in between reactants and products? No. There's so many ways you could get this. If you knew an energy diagram, you would know. Nope. If you remember my hand thing, you would remember it.
Oh,
Yeah.
oh my gosh, the what do you call it?
Yeah, but what is that middle part, right? These are the reactants and this is the product. What's in the middle? Anybody at home? Well, it's the next word. The activated complex or the transition state, which are the same. The transition state, remember, has a 50% chance going to products or back to reactants, right? So the activated complex is the transition state. It's an intermediate between reactants and products. It's what's formed right up here. If they have the activation energy, they can form the activated complex. Remember, this is the reactants, this is the products, this is where the activated complex would exist. It can go back this way, or it could go forward to the reaction. Once it's formed, using the collision theory, why does increasing temperature increase reaction rates? You guys did that earlier. You said moving faster. Thus, more energy. And they will collide more often because they're moving faster. More collisions, faster rate. How does a catalyst increase the reaction rate? What does it do? Good. And what is the overall action that does? It lowers the activation energy. By making a different pathway for the reaction. For a particular reaction, when the concentration of A is doubled, the rate increases by a factor of 4. What is the order of A? Right? You guys have the math stuff down. Referring to the same one above, how would it change if the concentration is tripled? 8, right? Not 8. No. Its order is 2. If we tripled that, it would be 3 squared. So that's 9, not 8. You keep switching that, and now you're making me switch it. Let's make sure we see this then. So rate equals Ka. If we have 2A here, like right now, the rate equals K times A, right? If we have 2A there instead, if we change that to 2A, then the rate will equal what? K and 2A squared. So that means that that will be what? Yeah, 4A squared. K 4A squared. Right? So its order is 2. So then if we have rate equals K 3A squared, what is it now? K 9A squared. So it's 9 times faster. Good, good. If a large percent of the molecules have the necessary activation energy, what do you know about the rate? What's going to happen if a large percentage has the activation energy? It can be fast or slow. Faster, right? If they already have the energy, then it's going to be faster. Given the data below, calculate the average overall rate of decomposition. So here's our change in time. And here's our change in concentration. We want 1.5 times 10 to the negative second minus 0.95 times 10 to the negative second. You get 0.055 for that. We're going to take 0.0055. That's the change in concentration. And we're going to divide that by the change in time. So we get molarity per second divided by 30. The rate then is 1.83 times 10 to the negative 4.
How did you get the 0.0055?
So it's overall average rate, right? So what's the overall mean? It means over the whole 30 seconds. Yeah?
Yeah, did you divide it?
Which we started with, and this is how much we ended up with. So how much went away? We subtract these two.
Oh, you subtracted it.
Yep. So that's the average overall. And there's our molarity per second. And this is calculate during interval from 10 to 30 minutes. I'm sorry, this is 30 minutes, not 30 seconds. So that is min. There we go. So 10 to 30, how much time goes by? 20 minutes. And then we want to take 1.29 times 10 to the negative second. What a weird way to write scientific notation. That's not a normal way. And that we get 0.0034. .0034. What is .0034 divided by 20? Nope, not for this. This is the first this is the first way we found the rate. So we get 1.7 times 10 to the negative 4 polarity per second. Per minute, dang it. Thank you. Are you not getting the .0034? What are you getting? .29 times 10 to the negative second, right? Minus. You're subtracting the, because which of these is the bigger number? When do you have more of the reactant? Earlier on, the more of the reactant, right? So this is the final amount of the reactant you have, so you have more at the start. Remember, this is, we're determining the reactant going away. Then we want to minus from that 0.95 times 10 to the negative second. 0.0034. For a reaction in which A and B react to form C, the following initial rate data were obtained. What is the rate law for the reaction? What does the rate law have? A, B, and C. A and B react to form C. The rate law only has what in it? A and B react to form C. What does the actual rate law have in it? A and B only, so it's only the what? Reactants, right? This is what you were talking about, Ian. That's the thing. If you don't do enough of these problems, then yeah, tomorrow you're gonna be like, that's doubled, and that's doubled. So what's the order for A? So 1. This is doubled and the rate doubled. So 2 to the x equals 2, x equals 1. Here it doubles, and here it quadruples. So that's doubled and to the 4th. So what is the order of B? 2. What is the overall order of B? The overall order is 3. So there's our rate law, but they want us to find K as well. How do we find K? Well, we take 8, and take trial 3, 8 divided by 0.2, divided by 0.2 to the second. Got 1,000. So the rate law, the rate equals 1,000 A B squared. Issues. So what will the rate be at the same temperature if our concentrations do this? That's interesting. Yeah, I don't know. That may be a mistake. You can't really have a negative. Hold on one second. Instead of being negative 0.55, it should be 0.55. Sorry about that. Sorry I didn't catch that before you guys worked that problem last night. But since nobody called me, I'll never know. Figured that, right? So we have 0.55 and 0.67. So what do? We take 1,000 times 0.55 times 0.67 squared. What do we get? We get 247. What's the rate? Molarity per second.
Is rate like, does it not matter if it's negative or not? Oh, you changed it.
No, yeah, we said that negative right there, somebody accidentally, instead of putting 0, they hit the negative key.
Okay.
They're right next to each other on the keyboard. For this? Yeah. Yeah, but here we were doing the product formation. Here we're doing the product formation. That's the formation of products, so that's going to increase as we go down. Here we're doing the reactant disappearing. You can do either. When you're calculating rate, you can either watch the reactant disappear or you can watch the product form. Well, what side of the reaction is this on? And what are those on the left side? What's the left side of reaction? Reactants or product? Reactants, right? So we're going to watch the reactants disappear as time goes on. Here, what side of the reaction is this on? Products. So that's product formation. The other thing is you can look at the numbers. These numbers are going what? Up. And these numbers are going down, right? Products disappear. I'm sorry, reactants disappear and products form. All right, bunch of questions on this thing. Determine the rate law. Well, it looks like it's rate of equals K, A, B. I have to do some looking here. Here's a decent one, 0.02 to 0.04. What happens to it? Doubles. And 2.8 to 5.6 doubles. So for A, it is 1. Now we got to find, I'm sorry, for B, it is 1. Now we got to find it for A. So we got to find it where a change occurs in A, but a change does not occur in B. 0.06 and 0.09. All right. So I take 0.09 divided by 0.06. I get 1.5. 1.5. And take 5.67 divided by 2.52. I get 2.25. So what do I need to do? I don't know what 1.5 to the x equals 2.25. Do you? You do? What do? We take the log of 2.25 divided by the log of 1.5. Hey, we get 2. Nice rounded whole number. And that is the order of A. Now it says find the value of K. What do you want to use? Trial 6 or what? Let's use trial 1 so I don't have to. There. I'll make this like a big overreach thing. Let's use trial. It doesn't matter what trial we use, right? So let's take trial 1, 2.8 times 10 to the negative 6 divided by 0.2 square divided by 0.02 to the first. We get K is equal to what, 0.35? So what you guys got? We could rewrite that rate law equation like that. It says if A and B are both 0.3, at what rate is C made? So we need to basically find the rate by plugging in K as 0.35, then 0.3 cubed. 0.35 times 0.3 squared times 0.3. We get 0.0095 or 9.45 times 10 to the negative third. Molarity per second, or I'm sorry, minute. Does that make sense with this? Here we have 0.09 and 0.2. If both of them are 0.3, wouldn't it mean it would be faster? Because those are both higher concentrations. It should be. And it's almost tenfold. So that makes sense. What is the overall order of this reaction? Third order. Using experiment number 1, what is the rate if the temperature is changed from 500 to 520? What is the difference there? 20 degrees. So we need to double it once and then double it again. Whereas I think we determined yesterday you could multiply it by 4, right? That gives us the K. For every 10 degrees, K doubles. So that means we have, for trial 1, we have the rate equals 1.4 times 0.02 squared, 0.02 to the first. 1.4 times 0.02 squared times 0.02. That'd be 1.12 times 10 to the negative 5th. Still much faster. What happens to K if you increase the temperature by 10 degrees? You double it, roughly. Bada bing, bada boom. Yep. There you go. Questions from the studio audience? Questions from the viewers at home? It lit up over here during that whole thing. 8 notifications from my camera at home. What if my house is being robbed? Probably my cat just jumping around on stupid stuff. No name. Questions from anybody? Nope. Cat messing with the Venetian blinds.
Could we go over the different labels for the graph?
Yeah.
Please. Thank you.
So if we take a look at the front here, B here, actually let's do A. A would be the energy required for the reaction to progress. B is the, what is the term I want? What am I looking for? The potential energy of the reactants. C is the potential energy of who? Yep. D is delta H, or the enthalpy. Is this E? Is the activation energy of the reverse reaction. Is this endothermic or exothermic? Exothermic. It's lost energy. Delta H is negative. How would we write catalyst in here? So A, we start at the reactants and you go up this much to get to the activated complex. And then you lose energy until you become products. Products can then go in this direction. And it would take that much energy for them to form the activated complex. Not very likely to happen with this type of reaction, but it could. For example, if we put a lot of energy into this, right? How would we draw a catalyst in here? You got it. Thing about a catalyst, does it change delta H? No. It only lowers the activation energy of the forward reaction. Does it lower the activation energy of the reverse reaction? Yes, it does. It creates an entirely new pathway where you could go forward or backward there. Yep. Q. Good enough, Coco?
Yeah, thank you.
You're welcome. Mask is really getting me today. Not fun. That's all I got, guys. If you have questions, by all means, stick around. Otherwise, get out of here. Make sure you get your study on. And I'll make one of the best tests I have yet, right? They just keep getting better and better and better. No.